The quantum mechanical model of the atom replaced the Bohr model in the early 20th century, so it's the early 1900s. So technology-wise, things were still pretty primitive. Okay, automobiles were a big deal. Most people did not have electricity in their houses. The quantum mechanical model was revolutionary because we came to realize that electrons do not behave like particles flying through space. You cannot imagine them as little airsoft pellets or BBs, just on a small scale. They don't act like that. The Bohr model had orbits, which are like the orbit of a planet around the sun. The quantum mechanical model has what are called orbitals. The words are very similar, and in some ways it's unfortunate because we can easily get them confused in our mind. An orbital is really not at all like an orbit. An orbital is really a probability map that shows a statistical distribution of where the electron is likely to be found. Now, in my, little cartoon imagination of how things are, I think of electrons as being just squirrely, little, unpredictable creatures. Because you just cannot predict where they're going to be. And an orbital just tells us, okay, it's probably in this area, but it's not necessarily. So let's compare baseballs and electrons. So the pitcher pitches a baseball, and you can predict where that baseball's going. You could even, you could take a picture or photography and you could draw it out, and you could predict exactly where it's going to go and how fast it was going and all this good stuff. Trajectory and the effects of gravity and wind resistance and all that good physics stuff. If you threw an electron like a pitcher throws a ball, even if you threw it exactly the same way every time, it would end up in a different place every time. That doesn't make sense, does it? If a pitcher pitches a baseball and he throws exactly the same way each time, the ball goes exactly the same place. That's what a good pitcher can do. They can put the ball right in the glove every single time. If you did that with an electron, it would not go into the glove every single time. It might go in there once, and it may never go in there again, even if you threw it exactly the same way. Electrons, as well as photons, have what we call wave-particle duality. They act like particles in some ways, and they act like waves in other ways. So in order to describe the behavior of that pitched electron, about the only thing we can do is construct a probability map. Pitch the electron, see where it goes. And so this is a probability map. So, one time it went here, pitch it exactly the same, this time it's over here, next time it's here. So each of these dots, it's like throwing at a target, or, shooting a BB at a target, except it doesn't go the same place every time. You shoot it in the same place, same velocity, same trajectory, but it goes somewhere else. And so these are like bullet holes in the target. But you see after a while that most of the time it's here in the center of it. But occasionally, it's way out here. And could it be up here once in a while? Yeah, it could. It's going in this general region, but we can't say exactly where it is. We can just say, well, it's probably here. So an orbit from the Bohr model is a circular path that shows the electron's motion around the nucleus. It's predictable, just like the planets orbiting the sun. We like that. We can understand that. An orbital is a probability map. It shows relative likelihood of an electron being found at various locations. It's completely unpredictable. It's statistical. So this is a little bit like my son Andrew. He's not quite as squirrely as he was, thank goodness. So this is, roughly a picture of my house. Okay, and then the whole blackboard there is the yard. And so if you were to see where's Andrew, we'll make him red. So red's kind of a color of caution, right? So, over the course of a day, maybe just see where's Andrew. And so maybe, the first time Andrew's here, and then another time Andrew's over there, and then he's over here, and then he's over there. And if you kept doing that, you would see that he's over here near the TV and near the table fairly frequently. He prefers my bathroom to the hall bathroom. He likes to sleep in my bed, but sometimes he sleeps in his bed. But then, he's not necessarily inside the house. There are times when he's not even on the property. When he was 2, he stole the neighbor's big wheel and rode it 3 blocks to my brother-in-law's house, which gave us, quite a scare. But that's kind of like what electrons can do. You don't know where they are. You ever see those Family Circle it's a comic in the newspaper, and occasionally they'll see, they'll follow Billy and they'll show him and his little path of where he goes around the house and all of his adventures and over the fence and spilling the milk and all kinds of stuff. It's a little bit like that. It's random. It's not an electron traveling in a nice orbit, a circular orbit around the nucleus. It's this thing going all over the place, and you never know where it's going to be. And if you find it here, the next second you don't know where it is. Okay, so this is a little bit like what electrons do. We could call the electrons Andrew.